We have silicon material, and it comes in two types, N and P. The N material is negatively charged, the P material is positively charged. And what we're going to do is we're going to mate them up. We're going to put them together. And when we do that, we're going to create what's called a diode. Oh, let's do this the other way. We'll put a wire on each side, and we will mate them with a barrier right here. And this will be called the depletion layer. This right here will be where the electrons stack up on one side and the positive empty holes on the other side. We're going to have to bias that particular junction. Before we do that, let's go ahead and look at what this looks like in a schematic. So here's a diode. A lot of times it'll have a circle around it. The current in a diode always flows against the arrow. That's how I always remember it. Forward current. If I forward bias my diode, forward bias, the current will flow against the arrow. I'll call it D1, and that's what it'll look like. Now, if it has an arrow through it, like this, then it's a lead. We'll talk about leads in a minute. We're just going to talk about diodes. Now, reverse bias stay up there. I will not flow. Reverse bias. Now, if I push it hard enough, it'll actually destroy the diode. So there's two things that destroy a diode. Too much current and reverse bias. So let's say my diode is a 1 amp diode. Notice I don't really care so much about the voltage. I might say it's 12 volt. But I do care about the reverse bias, so I'm going to say it has a reverse bias of 200 volts. That becomes really important when I build a power supply because I'm going to rectify the AC to DC, and I want to make sure that when it goes in reverse bias, it doesn't destroy the diode, okay? So could I use 120 volts on this? Absolutely. Will not overcome the reverse bias. Now, if you overcome the reverse bias, it does what's called avalanche, and it burns up in a hurry, and I've actually seen pieces pop off and hit people in the forehead. So when they go, okay? So I got one that's 1 amp. So now I know that if I forward bias my diode, I'm going to be able to flow up to 1 amp. If I go over that, I'll burn the diode out, okay? It doesn't burn out quite as violently if you do it forward bias as it does if you do a reverse bias, okay? All right. So, the diode looks like a wire in forward bias. In other words, it's like a one-way valve. It goes forward, but it won't go reverse. Why would that be important? Well, let's just think about a solar panel and a set of batteries. If I had a solar panel and a set of batteries, and I just hooked the wires right to the batteries, it'd be great while the sun's shining, the solar panel's making power, and it's going into the batteries. But what happens at night? Then the batteries power the solar panel, and it wastes all the energy you put in, right? So what I do is I take my solar panel and I attach it to my batteries, but I use a diode in my circuit so that as soon as the sun goes down, current won't flow back, right? I got it covered. There is a little loss in a diode though. In fact, to forward bias a diode, you're going to need 0.7 volts. In other words, if you start at 0 and you're headed to 12 volts, there will be no current flow until you get to 0.7 volts. At 0.7 volts, then you'll see the diode start to flow current. And it will flow current up to 12 volts or whatever voltage you stop at, as long as it's less than what destroys the diode, okay? So the current will start to flow. So you always have to take into account that 0.7 volts. It's called the forward bias voltage, okay? And if you don't, when you do your calculations on your power supply, they will be wrong. We're going to do a lab today that actually shows that 0.7 volts. Now, germanium diodes are lower, and we still use some germanium diodes and some diodes called pin diodes because their forward voltage is about 0.3 volts. So it's much lower. Turns out if you're going to do, let's do it over here. You're going to build a circuit. Remember how we talked about, oh, this thing's out of whack. Great. Not doing it there. I'll have to reset that. Okay. So remember when we did inductor capacitor circuits for, and we made this adjustable, right? Remember how we adjusted it to a certain frequency? We talked about adjusting it to, say, 880, which would be a radio station, kilohertz, here in town, right? So once it was adjusted to that, then we could take that output and actually do something with it. It would be the strong output, right? If you build a crystal set, little radio set, that's what you do is you put the diode across there, and at 0.3 volts, it's low enough forward voltage so it'll act as a detector. The silicon won't, but the germanium will, okay? And then you just put a headset on it, and then you can hear a radio station. So they're very popular for things like that. Detector circuits in a lot of different radio equipment have germanium diodes or pin diodes in it, okay, or various other types of diodes, but diodes that have a low forward voltage, 0.3 volts, okay? If you're going to do rectification, you're going to end up with silicon diodes in the power supply, and you're going to have to account for the 0.7, or if you have some combination of rectifiers, we're going to talk about those probably this next week, you might have to account for double that because of the way they're constructed. And so you always have to account for this right here when you're looking at a diode, okay? We don't want to put too many of them in our setup here. We don't want to put a whole bunch of these in here because every 0.7 comes off of the voltage that's charging the battery, okay? And you get enough of them in there, pretty soon you can't overcome the bias and it won't charge the battery. Okay, so why would you put that many in? Well, I don't know, but it happens. Okay, so, all right, so if we move through the book, you notice that's all there is on diodes on silicon and silicon junctions. Now, the next chapter actually shows the junction. Go to page 209, and you'll see the depletion layer on, well, 208, you'll see the depletion layer, okay? You'll also see that they show the negative and the positive charges, the electrons and the holes, and the migration with a battery and a limit resistor. If you go put a battery on it, a power supply, make sure you got a limit resistor on it, which we're going to do. Okay. On the next page, it actually proves that it's 0.7 volts at the depletion layer. That would be 210, okay? And it shows current flow, right? What happens to the depletion layer is as you get closer and closer to the 0.7, it gets narrower and narrower until finally the electrons can come across. And then it looks like a wire. No loss at all, okay? But as long as you're below that 0.7, no current flows. It's trying to build up enough electrons at the depletion layer and make it small enough so they can get across, okay? Depletion layers are important because it's going to happen with transistors too.